going through these 4 different scenarios. This is in our equation sheet. This is section 12, structural analysis. As you can see, these are the beam formulas. And so these are our shortcuts. All of these shortcut equations, they're derived from the static equilibrium equations, right? And so basically, they have it set up where this is the very end result here for you. And so we're going to be using these very consistently as we're going through these practice problems. If you end up having a scenario like this where it's a concentrated load that is symmetrically placed right in the middle there, then we'd end up using this equation to find those reaction forces at point B, which is vertical, and then also that vertical reaction force at point A. If you end up having scenario 2 here where it's this uniformly distributed load, you're going to end up using this equation to find the reaction force that's at point B as well as point A. You can see that both of these are equal to each other, right? So RA equals RB, and then it's just this equation here. It's the same case up here as well because these are symmetrically placed loads, right? It's the same case actually for this guy right here. This would be the case where you have a force that's located right here at distance A, right? So we might say A is equal to 2 feet, right? Well, it'd be the same case where this force is also placed 2 feet away from that support because that's also A, right? And then we have the total overall length. And in this case, it actually works out pretty well where your reaction force is actually just equal to one of these forces, so one of the concentrated forces there. And then this is the last scenario. This guy right here, this is our 4th scenario. Now, this is the case where we have this distance A, right? Could still be the case where A is equal to 2. And then if the total distance is 16, well, if this was 2, that's 16, then this must be 14. Basically, what we end up doing is we just plug in all those known values, right? So if P was equal to, say, 200, B was equal to 14, the overall length was 16, then you'd plug in all those values to find out what that reaction force is going to be at point A. Remember, that is a vertical Y force. And then to find B, it's basically same process, right? We need to take P times A, in this case, which is right there, and then divide that by L. But what I want to do here is I want to show you guys how we end up getting to these equations here. And so I'm going to start from the basic static equilibrium equation, and we're going to work our way to get to this beam shortcut formula here. So let's go ahead and let's start off with scenario 1. So scenario 1, this is how we end up getting that beam shortcut here. So for scenario 1, it is the case where we have this beam, right? And they just tell us it's a length L. So we'll just go here. And then it is the case where we have pin supports for all of these, right? So as you'll remember, a pin support has an X component force as well as a Y component force for the reaction. So I'm just going to go ahead and put in here R, A, Y. And so that's for reaction force at A, and it's the Y component. We're also going to have the reaction force at A, and there's going to be the X component. And then now whenever we look at this roller, for rollers, there's just the Y component of the reaction force for those. They only supply a Y component. And so now we've also got it where there is that concentrated force P, and it is the case where that is placed. If this is L here, some distance L, this is actually placed halfway, so we can represent that as L divided by 2 here. And so now we're going to work our way towards this beam shortcut. What we always want to end up doing, what I always like to end up doing is I like to start with the sum of the moment. Now, for the sum of the moment, we want to always choose the point that has the most unknown forces. So as you can see here, we have RA, the reaction force at A, and that actually has 2 unknown forces. So if we end up doing that, it's going to help us out. So sum of the moment at A. Now remember, we want to end up ensuring that clockwise rotation is negative. So counterclockwise is positive. That's a standard convention, right? As long as you end up, whatever you put down here, as long as you end up following that convention, though, you're totally fine. That's what's awesome about physics. But anyways, I got to think about this for a second because I think you guys are actually the opposite of me. But yeah, it will be the case where if we rotate this way, right, if our beam rotates this way, then that's going to be positive moment. And so we can end up looking at this. We have this reaction force A, we have P here. And so what we can imagine is if this is where we have our hinge, if we have some force P acting on this, let me get a little pencil so that I can simulate this force so that my big fingers don't get in the way. But if we have this force P acting on this beam, as you can see, if it's hinged on A, that is going to cause counterclockwise, or sorry, that is going to end up causing clockwise rotation, right? So that's going to be a negative moment. So we put a negative sign there, and then we have to take our force multiplied by the distance that's perpendicular. So we're going to end up with P times L divided by 2. Now, we aren't plugging in any numbers in this because we're just trying to get we're trying to solve for this in terms of variables. And then so now, if we also have our pin be the beam and we have the hinge about point A because we put the moment as being calculated about A, if I end up coming in here and I apply this reaction force B, as we can see, that is going to be counterclockwise rotation, how our pin's moving. So it's going up this way, right? So that's following this direction in terms of that curvature or rotation. So that's going to be positive. And then we can take RBY times our total length of the beam, right? Now that's going to be equal to 0. The reason why we're not taking into consideration these forces is because if we're calculating this about the moment about A, right? These forces are being applied directly on A. So whenever we take their distance from A, it's going to be 0, right? And so that's why it is always in your best interest to calculate the moment about the point that has the most unknown forces acting on it. But anyways, what we can do now is we want to solve for RBY. What they end up saying in the equation formula or the formula sheet is just RBY is RB simply. But anyways, what I can end up doing here is we can add P times L divided by 2 to the other side, right? So that'll cancel. So I got P times L divided by 2. And so now we have RBY, and then we have multiplied by L is equal to P times L divided by 2. And so now if we want to solve for RBY, we can divide by L. We can divide by L here. As you can see, the L's cancel on this side. They're also going to cancel on this side. And so then we're left with RBY is equal to P divided by 2, right? And so that tells us that RB is equal to P divided by 2. Now, if we look back on our equation sheet, you can end up seeing RB is equal to P divided by 2. Now, what I want to show you is how we can find out RA is also equal to that value. So what I can look at now is we can look at the sum of the forces in the y-axis. And we're going to set those equal to 0, right? Because this beam is in static equilibrium. I'm also going to specify that up is going to be positive. And so now I can take all the forces that are acting in the y-axis. Isn't RAY acting in the y-axis? Yep. RBY also acting in the y-axis. P is also acting in the y-axis, but it's negative, right? Because it's going down. RAX, it is not acting in the y-axis. That is just acting solely in the horizontal plane. And so that's an x-axis force. So we're not going to include that one. But we got positive RAY because it's going up, positive RBY, and then we've got negative P. And those are all equal to 0. Now, in this scenario, I can add over P so that RAY and RBY are by themselves, right? And what we can also do actually is let's go ahead and subtract RBY. Now, why am I doing that? That is because we already know what RBY is in terms of P, right? So now what we've got is RAY is equal to P. Now we've got P here minus, and then RBY, do take note, RBY was equal to P divided by 2, right? So can't I just replace P divided by 2 instead of RBY? We could end up replacing P divided by 2 for RBY. And so now we have RAY equals P minus 1/2. Now, what you can always imagine is that there's a 1 right out here, right, in the front of this. Now, if you take 1P minus half of P, that's like 1 minus 0.5, right? What you're going to end up with is just P half, right? So half of P. So now what we just basically proved is that RAY is equal to P divided by 2. Well, what else is also equal to P divided by 2? RBY. And so that's how we end up getting to this point where RA, let's say, right, instead of RAY, it's just RA is equal to RB, which is also equal to P divided by 2. And so that's how we end up getting to the point of we get to that shortcut 12.1. Now, the last thing I need to do here is I do need to prove that this is equal to 0, though, before we move on. So let's go ahead and let's do that. I'm going to calculate the sum of the force about X. We're going to make to the right be positive. So any forces acting to the right here is going to be positive. So we just have RAX, right? No other forces are acting in the x-axis. And so therefore we can prove that RAX is 0. And so we don't have to take that one into consideration. And so that's how we just have RAY equals RBY equals P divided by 2. Okay, so just remember, these are the Y components of those reaction forces. All right, so that's scenario 1. Let's go ahead and let's move on to scenario 2 here. So scenario 2. So I'm going to go ahead and start by creating the free body diagram, right? So we have the uniformly distributed load. Remember, W, that is the uniformly distributed load that we were solving for in 322. That's where it's tributary width multiplied by the total load, right? And so now we can end up setting this guy up. So what we'll end up doing here is we're going to write this out. So I'm going to go ahead and place this guy right here. And we're going to go right here, boom. And then so now the uniformly distributed load is basically per foot, we're going to have a certain force that's applied, right? And so that's W there. And then what we also have is point A here. So remember, this is a pen that we have here. So it's the X component. There's also the Y component. And then over here is just a roller. So that's just RBY. And then we have this distance here, which is L. And W is just applied consistently throughout this, right? So we're going to end up doing that. Now, this is kind of the exposure here is kind of bad. Let me see if I can end up maybe using my phone flash so this will automatically kind of adjust maybe a little bit better. It's kind of giving us a little bit of a hard time. But anyways, maybe I can kind of adjust it afterwards. So now we've got this uniformly distributed load. What we're going to end up doing is we're going to have to end up making an approximation. And so we'll kind of talk about that for the sum of the moment. And so let's go ahead. Let's start with the sum of, actually, let's start this one with the sum of the forces in the x-axis. So I'm going to say to the right is positive. Sum of the x-axis forces is equal to 0. All we've got in this one is just RAX, right, acting in the x-axis. And so that's how we know that that one is equal to 0 just from the get-go. So what I'm going to go ahead and do is I'm going to set that equal to 0 there. All right. What I'm going to try to do, maybe I'll zoom out a little bit here. Maybe that'll kind of help. Maybe not. Okay. So anyways, we know that that one is equal to 0 just from the get-go. Now what we can start to look at is the sum of the moment. Now I'm going to choose, it's up to me, right, to choose either of these 2 points because of the fact that we said RAX is equal to 0. These both have the same amount of unknown forces, so it's really not in any particular interest that we choose. There's no bias here, right? So we could just choose B. Let's choose point B, and we're going to say that that's equal to 0. Now we're going to have counterclockwise rotation being positive. Remember, that's our standard convention. And so now what we can end up doing here is we can end up calculating the moment about point B. Now, what we end up doing is we basically make an approximation here. We want to approximate this uniformly distributed load as a concentrated load whenever we're calculating the moment. And so since this is uniformly distributed, if I wanted to take an average, I can place this as a concentrated load in the middle, right? And so that's what we end up doing. So it's going to look something kind of like this. Let me show you guys. So it's going to actually be where this is approximated, where this is a uniformly distributed load P. Now, P in this case is going to be equal to omega times L, right? In that case, because we have to take this uniformly distributed load, remember that's a pound times feet, multiply that by the feet that it's applied for, that ends up giving you a unit of pounds. And so that's why we have P is equal to W divided by L. Now, it is the case where this guy is placed L divided by 2, so it's half of the distance in, right? And so this kind of helps us out here as we're trying to calculate the moment. We have to just approximate this as a concentrated load that's placed in the middle because this is uniformly distributed. So let's go ahead. Let's look at this. If we have RB, let's first start with RA. So we're going to have that reaction support that's going to be right here. Now, if I look at this, this is going to cause that clockwise rotation of the beam, right? If we have that force. So what I'm going to do is I'm going to put negative, and then we got RAY. We're going to multiply that by L because the distance that that force is applied from our point that we're calculating the moment about is L. And then what we want to end up doing is we want to think about this uniformly distributed load as an approximated concentrated load, right? So if this is point B here still, we have this force P, which is that approximated force, concentrated force. And as you can see, that's going to be counterclockwise rotation. So that's actually going to cause a positive moment. And what we want to do is we want to take that force, well, P, we can represent that in terms of W, right? Where we have W times L. And then now what I want to do is I want to multiply the distance that is from the point we're calculating the moment about, right? Well, if this whole distance from here to here is L, that tells us that this distance from here to here is L halves, right? Because this is a half of L as well. So we're going to take L divided by 2 here. And then so now we want to think, are there any other forces that are acting on this? Well, we took into consideration RAY. We took into consideration that approximated force, right? Or this uniformly distributed load as a approximated force. And so now there's no other forces that are causing a moment on this beam. So that's equal to 0. Now what I can do is we can end up solving for RAY, right? So what I'm going to do is I'm just going to add RAY times L to both sides so that then we're going to end up with omega L times L halves is equal to RAY times L here, right? And so now what I can end up doing is I can divide this by L. Now, if I divide both sides by L, you'll see that those L's are going to cancel. Then we're going to be left with RAY is equal to omega L, which, guys, remember, omega, I'm just using that in place of W there, the uniformly distributed load. And that's going to be divided by 2, right? So WL divided by 2. And so let's check this out. Does this line up? Does this match with RAY? In this particular scenario, yeah, RA is just the Y component of the reaction force, right? And it's equal to WL divided by 2. So we are on track for this, right? Now, what we need to determine, though, is, well, what's RB, right? We want to find out what RBY is. So there's different ways you could go about this. You could calculate the moment about point A now instead of point B to find out what RBY is, or we can just end up doing this. The sum of the forces in the y-axis is equal to 0. I made up positive. We have RAY acting in the positive y direction. We have RBY acting in the positive y direction. And then we're going to have this uniformly distributed load that we can approximate as a force. It's going to be acting in the negative y-axis, right? So I'm going to minus omega times L. So omega times L, that's going to be equal to 0 here, right? And so now what we can end up doing is I can add omega L onto both sides. And then what we end up with is RAY now plus RBY is equal to omega times L, right? And so now as we move forward with this, I can subtract RAY to the other side. So RBY is going to be equal to omega L minus RRAY. Well, remember, RAY was omega times L divided by 2. So can't I just replace that in there instead of this being RAY? Well, that's what RAY is equal to. So it's actually RBY is equal to omega times L minus omega times L divided by 2. Well, once again, guys, this is like where there's a 1 out in front here, right? If it's 1 omega L minus 0.5 omega L, these are the like terms here. So what ends up happening is that this becomes omega times L divided by 2, and that's a positive omega times L divided by 2. And so now, just as we can see here, RAY and RBY are both equal to omega L divided by 2. And so that's where we end up getting that RA equals RB equals omega L divided by 2. So there you have it there for scenario 2. I'm going to go ahead and get a new piece of paper, and then we're going to go through scenario 3 and 4. We end up having this where it is a symmetric, 2 concentrated forces being placed symmetrically on our beam, where they are both at distance A away from these reaction locations, right? And so what we can end up doing is we can create a free body diagram of this. Once again, location A, that was a pin, so we have RAX as well as RAY. At point B, we're going to have RBY here. And then what we're going to have is P, and then as well P. Now, this is the case where both of these forces are equal to each other, right? This is just literally P. So it's not P1 and then P2. If we had a P subscript 1 and then P subscript 2 over here, that would be the case where these are different forces. These forces are actually both the same value here, right? And so both of those are located a distance A away from these supports. And then our overall distance is just L here, okay? So now that we have the free body diagram, let's go ahead, let's get ready to begin. What I'm going to do first is I'm just going to start off with some of the forces in the x-axis. Remember, positive is over to the right. RAX, that's the only force that's acting in the x-axis. And so that's how we know that RAX is equal to 0. So this guy basically just gets taken out there. So next thing that we want to do, we could go ahead and calculate the moment, or we could end up finding the some of the forces in the y-axis. If I find that some of the forces in the y-axis, do take note, these two are unknown. So what we want to do is we want to solve for these reaction forces so that we get them in terms of P. If I calculate the moment first about either point A or point B, that'll actually allow me to be able to solve for one of these variables, because remember, if we calculate the moment about A, this force is no longer going to be taken into consideration because that force is actually acting on that point A. So the distance that this force is acting from point A is just 0. So that's how that moment cancels out. So let's go ahead and let's do that. Let's calculate the moment. Now I'm going to choose, let's just do point A, and that's going to be equal to 0. Now remember, counterclockwise rotation is going to be positive. And so now what we can be thinking about again, imagine your pencil is the beam. And if you ended up having this force here, RBY, acting on this, you would end up finding that that is counterclockwise rotation, right? And so that's how we know that this is going to be a positive moment caused by RBY. So RBY multiplied by the distance that force is being applied from to the moment or the point we're calculating the moment about. It's going to be L, right? And then so now it's going to be the case where we're going to have two of these forces acting, right? And so if I end up simulating this, if my pen's the beam, I have this force here that's being applied. You can see that my pen wants to rotate clockwise. And so this ends up becoming a negative. And then what we've got here is it is going to be the case where we end up having, let's see here, this is going to be where it's going to kind of end up getting a little ugly here. So this is going to be L minus A. So we got that force P multiplied by L minus A, right? Because that's L. If I have L minus A, it means we're going to go back this distance here. And then what I also need to take into consideration is this force P as well. Now this force is also going to end up causing clockwise rotation on this beam, right? So we can do minus, and then we just got P times A there, right? Now, those are all the forces that are going to be causing a moment. So we can set this equal to 0 here. What I want to do now is start to solve for RBY. So what I'm going to do is I'm going to add P times L minus A. Now, we can do this. We'll simplify this later. Minus PA, so plus PA. That's going to cancel those guys. It's going to cancel that. Then we have over here plus PA. And then we have also plus P times L minus A. This is where I probably should end up moving down here so we got a little bit more room. But anyways, let's go ahead and let's put this guy out here. So then that's going to be equal to PA plus P times L minus A there. Now what we can do is we can end up distributing this guy out, right? The P times L and then P times negative A. So we got PA plus P times L minus P times A. Now, these are like terms, right? What ends up happening? Well, if we have a positive PA and then minus PA, it's going to actually cancel out. Then we're left with RBY times L is going to be equal to PL. Now, if I divide this side by L, I can also divide this side by L. So we get RBY by itself. And that's how we end up getting to the point where we find RBY is going to be equal to P. All right. Now, what we have not proven yet, though, is that RAY is equal to P, right? If we look back on our equation sheet for scenario 3 here, should be the case where RA and RB are both equal to P. And so now what we can do is we can put this in the positive. Sum of the forces in the y-axis is going to be equal to 0. And so now we can look at all those forces that are acting in the y-axis. Well, we have RAY, we have RBY, those are both positive, and then we have a negative P and then a negative P again here, right? Because both these P forces are acting in the negative axis. So let's go ahead and write these out. RAY plus RBY minus P is equal to 0. Now, these are like terms, right? So that's going to end up being a negative 2P. What I'm going to do is I'm going to add 2P to both sides so that then we can end up getting RAY plus RBY is equal to 2 times P. Now, in this case, we already solved for RBY, right? So we know RBY is equal to just P, right? So if I subtract RBY from this, and I subtract RBY from this side, we're going to end up with RAY equals 2P minus RBY. Now, didn't we say that RB was equal to P? So then now let's just go ahead and rewrite this. It's going to be 2P minus P, right? Now, if we have 2P minus P, that's 2 minus 1, right? Which is 1P. And so now this is how we just ended up proving, well, RAY is equal to P as well. And so just like in our formula sheet, therefore we can say RA is equal to RB because those are both equal to the same values, right? P. So we'll place that in there. And that's how we end up getting to that point where we can solve for these reaction forces RA and RB with that beam shortcut. So that's where that comes from. Let's go ahead. Let's move on to scenario 4, which is going to be the last scenario here we're going to be showing y'all. Last shortcut. So scenario 4, we have it where there is just a concentrated force being applied and it is not symmetric. It is a certain distance A away from this reaction point A, and then it's a certain distance B from reaction point B. There's also this overall distance L. So we're going to go ahead and create that free body diagram. I'm going to go get this guy. Remember, this is a pin over here on this side, so that's RAY. This is RAX. This is RBY. And then if this is where our concentrated force is being applied and that's distance A, this is going to end up being distance B, and A and B are going to add together to get us to L, right? So let's go ahead. Let's move this guy up just a little bit. So now, remember, this is A and this is B. I'm seeing it's a little pixelated on here. But anyways, now we can look at the sum of the forces. Let's go ahead and prove that RAX is equal to 0. So sum of forces in the X, this is the only X component. So RAX is equal to 0. And so we can cancel this guy out, put a 0 there. There we go. And so now we can start to look at the sum of the moment. That's what I'm going to do again. So sum of the moment, we can choose either of these points. I'm going to go ahead and choose to calculate about point A. That's going to be equal to 0. Remember, we want to specify that counterclockwise rotation is going to be positive. And so now what we can do is we can calculate the moment about point A. What I'm going to do first is I'm going to end up simulating the beam. It is hinged at point A, right? Which is the point we're calculating the moment about. I'm going to go ahead and push on our beam at point P with a concentrated force. And as you can see, that is starting to cause our beam to rotate clockwise, which is going to be negative. So we're going to take the force, which is P there, multiplied by that distance A. And then so now what we can do is we can end up also simulating this reaction force, right, at RBY. So if I push up, it's going to be right there. That's going to cause counterclockwise rotation. So then it's going to be the case where it's going to be RBY times L, and that's going to be equal to 0, right? Because those are all the forces that are going to cause a moment on this beam. Now what we can do is solve for RBY. RBY times L is going to be equal to PA. Now what I can do is divide by L on both sides. What I end up finding is RBY equals P times A divided by L. Now let's make sure that that is the case for the equation sheet. There's a different way you could end up writing this out too, where we use B. But yeah, I see that they have RB equals PA divided by L. And so that shows us how we end up getting that equation right there. What I'm going to also do here, guys, real quick. So this can be 1210. Just going to write in those equation numbers. And then the last thing that we solved for was 12.7. I'm going to make sure that I'm pretty thorough with this documentation. We're going to also put in 12.4. So this was for scenario 2, right? This is how we end up getting 12.4. That's what that equation is right there. So I'm just going to take note of that. So that was 12.10 here that we just solved for. And then so now we can find RAY here. So how we can do that is we could use the sum of the forces in the y-axis is equal to 0. Up is going to be positive. And so now it is the case where we have RAY, which is a positive force, plus RBY, and then minus P equals 0. So now it's going to be RAY, and I'm going to solve for RAY here, right? So I'm going to minus RBY plus P, and then what we do to one side, we have to do to the other. So minus RBY plus P here. RAY is going to then be negative RBY plus P, which RBY we just said is PA divided by L. This is going to be a negative there, and then that's plus P. So then now what we can end up doing, there's different things we can end up doing for this. Let's see, how do they have this written out? They have it PB, P times B divided by L. So let's think about how we can end up rewriting this. If this is RAY, you could put, bring out a P. It's going to be 1 minus A over L. So we could do that. We could also think about how we could rewrite RBY. So RBY instead of A, we could also say RBY is equal to P times. Now, other way to express A is just being L minus B, right? And then dividing that by L. So we could do that too. If RBY is equal to PL minus PB divided by L, we could separate this where it's PL divided by L minus PB divided by L. Now, if that's the case, RBY is going to be equal to P minus PB divided by L. And so now, if we end up actually going back to just this equation right here that we had, we could plug in RBY into there. And so now let's go ahead. We're going to move up here. So RAY equals now negative RBY. That's these values right here, P minus PB divided by L. So it's going to make all of these negative, right? It's going to basically have a negative that's distributed. So I'm going to go negative P, and then this is a minus times a minus. That's going to make a positive PB divided by L. And then I've got to add on P at the end. And so what happens here is P and P cancel there. RAY is going to be equal to PB divided by L. And so that's how we end up getting this equation here for RAY by doing that substitution. And once again, this is just equation 12.10. All right. Now, just to recap on this, do you need to know these derivations? I'm going to tell you, no, you don't need to know them. Are they nice to know? Absolutely. Especially if you end up going into engineering, very important that you understand how we end up getting these beam shortcuts. Whenever you're in college, your equation sheet, I was a little bit more physics oriented for my engineering degree. But for us, it was the case where we just had the sum of the forces, right? We just had to use those static equilibrium equations. We weren't given these shortcuts here. So it could be the case for you, but it is always nice to know where we ended up getting these. So anyways, hope that video was helpful. I'm going to go ahead and end this. Thanks for watching. Happy calculations. See y'all later. Bye-bye.